In this video, I'll go over piecewise interpolation with splines. After studying this video, you should be able to explain how piecewise interpolation addresses some of the pitfalls of polynomial interpolation. Recall those two main pitfalls were round-off error because of the ill-conditioned van der Waals matrix and oscillations in the higher order polynomials. Should be able to describe different types of splines used for piecewise interpolation and explain why cubic splines are the generally preferred method of polynomial interpolation for most applications. Lastly, you should be able to understand how to calculate spline coefficients by solving a linear system of equations. So what's piecewise interpolation? So the idea here is instead of fitting a single n-1th order polynomial to n data points, we'll fit lower order polynomials to subsets of the data. So recall in a previous video, we fit a 10th order polynomial to 11 points. And we saw some problems with oscillations there. So instead of fitting a 10th order polynomial to fit through all 11 points, a piecewise approach would be to choose subsets of those points and fit lower order polynomials through those subsets. If the subsets are just 2 points each, then we're going to call these connecting polynomials splines. The most common connecting polynomials for spline functions are linear or cubic, and the points where the polynomials connect are called the knots. You can imagine it's where we're tying these different functions together at the data points. Splines minimize oscillation problems and reduce round-off error because of their lower order nature. So if you recall from our earlier discussion of polynomials, as we increase the order of the polynomial, we increase the round-off error problems and we increase oscillations near the end of our data set. If we just keep those polynomials lower order, like cubic, for example, we can avoid those problems. So let's look at how we can formulate a spline. So let's say we have a set of n data points. We'll have n-1 intervals between the points. So here's, say, 7 data points here, and we would call this the interval. And that interval, in this case, if there's 7 data points, this is between the 5th and the 6th data point. So we have 7 data points, 6 intervals, and we can imagine defining some spline function. We would call that, since this is the 1, 2, 3, 4, 5, 5th interval here, we would call that the 5th spline function, and it would be some function of x, and that is only valid between x5 and x6. And then we would define some other spline function over here, call this s2 of x, and that would be valid in the second interval between x2 and x3. So let's look at some example spline formulations. So this first figure here is a 6th order interpolating polynomial. So it's not a spline, it's just a 6th order polynomial going through all 7 points. And we can see some oscillations starting to develop near the endpoints in the range. So we can fit a linear spline through those same points, and it's simply like connect the dots, where we will just draw a straight line between each of the data points, and that gives us our linear spline. A cubic spline is going to look a little smoother. Notice it looks about as smooth as the 6th order polynomial, but one key thing here is no oscillations. So let's look at how we would then actually calculate the functions behind these splines. So for a linear spline, we're just going to find equations of the line for each interval that passes through the points at either end. So at each interval we have a point, call it xi, and another point, xi plus 1, and we're just going to find the equation of the line that goes between those 2 points. For a quadratic spline, now we're going to have a parabola, and a parabola is going to have 3 unknown constants. A line had 2. A parabola is going to have 3 unknown constants. So we're going to get 2 equations for those constants by making sure that parabola passes through the points at either end of the interval. And then we're going to match the first derivatives at the interior points. We'll call those, again, those are called the knots, so that it looks continuous. And that gives us the rest of our equations to solve for those unknown constants. Then for a cubic spline, we're going to find cubic equations for each interval. So those cubic equations will have 4 unknown constants. And to get equations for those constants, we get 2 equations by making sure the cubic passes through the points at either side of the interval. We get 1 more equation by matching the first derivatives at the knots, and another equation for matching the second derivatives at the knot. So this gives us 4 equations for each interval for each of the 4 unknown constants. There's a little twist there, but we'll get to that in a minute. So in general, cubic splines are preferred, and that's because they provide the simplest representation that exhibits the desired appearance of smoothness. So we get a nice smooth function that looks continuous, but it doesn't have the oscillations that we get from higher order functions. So if we used a linear spline, we've got discontinuous first derivatives. So at each of the knots, we have a kink in the spline. Quadratic splines are going to have discontinuous second derivatives, so we would have abrupt changes in curvature at the knots. They also, in their implementation, require setting the second derivative at some point to some predetermined arbitrary value that's just kind of not desirable. But if we were to go to higher order splines like quartic splines or 5th or 6th order polynomials, we're going to get those same instabilities that we're trying to avoid by going to piecewise interpolation in the first place. We're going to get ill-conditioned matrices to solve for the coefficients and oscillations. So let's look at how we can determine cubic spline coefficients. In general, we can write the ith spline function for a cubic spline as Si of x is equal to Ai plus Bi times x minus xi plus Ci times x minus xi quantity squared plus Di times x minus xi cubed. So just to illustrate what we're doing here, so let's call this Si of x in this interval right here. So we're setting up that equation such that it starts at xi, but we have to write the equation still in terms of x. So x is starting way over here from x equals 0. So here's our x. And we're going to formulate that polynomial so that it starts from xi, and then this, so xi again would be this distance from the origin to xi, and then the distance from xi to wherever we are within that interval, that's going to be the x minus xi. So that's why we have that x minus xi term as our main term in defining that polynomial. And then we just have the 4 unknown coefficients like we would have for any cubic. Now, for n data points, we're going to have n minus 1 intervals. So n minus 1 spline functions, and for each of those n minus 1 spline functions we have 4 constants. So we have 4 times n minus 1 unknowns to evaluate to solve for the spline function coefficients. So let's look at how we can apply those constraints we discussed earlier to solve for those coefficients. So we'll start by noting that the spline function goes through the first and last points of each interval. So that's going to yield 2 times n minus 1 equations of the form. So first of all, for the first point, we've got Si at xi is equal to ai plus bi times xi minus xi plus ci times xi minus xi squared plus di times xi minus xi cubed. So all of these terms go away to 0, and all we're left with, so this is equal to the value at that point, fi. So that's where we're left with this equation, ai is equal to fi. So we'll get n minus 1 of those equations for each of our ith intervals. And for the I plus 1 interval, we do the same thing, but we plug in, again, for the spline function for the ith interval, but evaluated at xi plus 1. So that's the right side of the ith interval. And when we evaluate that, we get a sub I plus bi times xi plus 1 minus xi plus ci times xi plus 1 minus xi quantity squared plus di times xi plus 1 minus xi quantity cubed. Now each of these are just going to be a constant once we plug in the data. And so we have a linear equation for ai, bi, ci, and di. And we'll get another n minus 1 of those equations. So we've got 2 times n minus 1 equations just by making each spline function go through the start and end points of its respective interval. Next, we need to apply that first derivative constraint so the spline function looks continuous at each interior point, or not. So let's start by calculating what does that derivative of the spline function look like. So ds dx, that's going to be the a sub I goes away, and we get bi plus 2ci times x minus xi plus 3di times x minus xi squared. And then we want to use that derivative for that continuity constraint at the naught. And so I'll plug in on the left-hand side xi plus 1 into si. So I get bi plus 2ci times xi plus 1 minus xi plus 3di times xi plus 1 minus xi squared. And then we're going to plug in, for the right-hand side, xi plus 1 into the I plus 1 spline function derivative. So that's going to be equal to bi plus 1 plus 2ci plus 1 times xi plus 1 minus xi plus 1 plus 3di plus 1 times xi plus 1 minus xi plus 1 squared. So that term goes to 0 and that term goes to 0. And again, we have linear equations, and this is for each interior point. So how many interior points do we have? If we come back here, we have, here's our 7 points, and then we have 1, 2, 3, 4, 5 interior points. So, and that will generally be the case, that if we have 7 data points, we'll have n minus 2 or 5 interior points. So this gives us n minus 2 more linear equations. And so we need to find some more. So let's go to the second derivative constraint. So first we can find the second derivative And looking back here, we can see the BI's are going to go away, and we're going to have a 2CI plus 6DI times the linear term. So we're going to get 2CI plus 6DI times x minus xi for our second derivative, and now applying it to our constraint equation at each interior point, plugging in xi plus 1 into the ith spline function, we get 2CI plus 6DI times xi plus 1 minus xi is equal to, and then plugging in the xi plus 1 into the I plus 1 spline function, we get 2CI plus 1 plus 6DI plus 1 times xi plus 1 minus xi plus 1. Again, this goes to 0. So again, what we're looking at here is this right here would be SI second derivative evaluated at xi plus 1. And then the right-hand side is SI plus 1, the I plus 1th spline function, second derivative evaluated at xi plus 1. So this is going to give us another n minus 2 equations. And so recall from the first equations we had 2n minus 1, just by making sure the spline goes through the first and last points of each interval, plus n minus 2 from the first derivative constraint, plus n minus 2 from the second derivative constraint, and that is equal to 4n minus 6 equations. But we need 4n minus 4 in order to solve for all of the spline coefficients. So we need 2 more equations. There's a few good options for those final 2 equations. One option would be natural end conditions. And for natural end conditions, we're just going to assume the second derivative at the first and last points are equal to 0. So that'll give us 2 equations of the form, again, here's our second derivative. So 2 equations of the form 2CI plus 6DI times x minus xi equal to 0 at the first and last points. So this is for I equal 1 and for the first point, and for I is equal to n for the last point. Sorry, it'd be I equal n minus 1 would be the n minus 1th spline, because we have n minus 1 spline functions. We can also use clamped end conditions. Clamped end conditions assume the first derivatives at the first and last points are known, and then we just specify values for those first derivatives. So recall that first derivative looks like bi plus 2ci times x minus xi plus 3di times x minus xi squared, and we're just going to set that equal to some constant, again, for I equals 1 for the first interval and x equals 0. Again, that's over here, x equals 0. And I equals n minus 1 and x equals xn, our last data point. Again, this was for x equals xn, our last data point. So those are 2 good options, and another option is what's called not a not end conditions. Explain why it's called not a not in a second. The basic idea here is to force continuity of the third derivative at the second and next to last knots. And what happens in effect when we do that, so if we go back here, we're going to say just at the second knot here and the next to last knot here, we will enforce continuity of the third derivative. And by doing that, actually the first 2 spline functions become the same. And the last 2 spline functions also become the same. And so it in effect negates that second and second to last knot. And that's why it's called a not in condition. So the best choice in terms of what you want to use for the in conditions, and this is something that you use when you implement splines in MATLAB, or actually go through the detailed calculation with numbers to find the spline coefficients, is going to depend on the particular data set that you're working with and the application that you're dealing with. And generally you might try a couple different options for the in conditions and see which one yields a result that seems most reasonable. And we'll see an example of that when we implement splines in MATLAB in the next video.